Revelator John.
Hello, welcome to Revelator John. What is the relationship between air temperature, pressure and volume with altitude? And how this can affect our bodies and how this can affect activities such as aviation. So if we consider the sun, first of all, in very basic terms, the Earth really receives all of its energy from the sun. So the sun, through its solar radiation, the sun's rays hit the Earth, heat up the Earth, and then as the Earth radiates its heat, therefore as it loses heat, it heats up the air surrounding it, and then that causes air molecules to start to become hyper-energized, and there's a lot more movement, and this causes expansion. Therefore, the volume of the atmosphere starts to increase. The volume will be greater at the equator because as most of the solar heating is at the equator. So you'll have an atmosphere over the equator about 50 to 60,000 feet, possibly more. Conversely, at the polar regions, there's a lot less solar radiation, therefore a lot less terrestrial radiation. Therefore, this will lead to less expansion of the atmosphere, so a lot less vertically developed atmosphere over the poles in the region of 20 to 30,000 feet. So we both have two volume areas above the surface of the Earth. Over the equator, it will be a very highly developed atmosphere. At the poles, it will be very low developed, vertically developed atmosphere. So one is a high volume, one is a lesser volume. So as we have a high volume of air above the equator, there is still a tremendous amount of a body of air that is beating down, bearing down on the surface. So at the surface level, we will have the full pressure of that air. At the poles, although it's not as vertically developed, the atmosphere, you still have the weight of an atmosphere beating down, bearing down on the atmosphere, on the surface rather. At the equator, the air is a lot less dense and a lot warmer, hence why it is expanded so much to create the more vertically developed atmosphere. At the polar regions, the air is a lot more dense because it is colder, hence why it hasn't expanded so much, and therefore you would have a high pressure system at the poles, and you also have a high pressure system at the equatorial regions around the equator. So at the surface, you will feel a certain pressure, both at the equator and at the polar regions. Both will be relatively high pressure systems. In the middle latitudes, in the tropical regions, the tropic Cancer, Capricorn, for example, you will have mainly the lower pressure regions. So the high pressures from the high volume areas of the equator will move towards the lower pressure areas of the tropic of Cancer and Capricorn. If we look at the polar region, it's a high pressure as well, but not from a more vertically developed atmosphere, but more from a lower developed atmosphere, but more colder, dense air. That will also move towards the tropics, the lower pressure areas of the Tropic of Cancer and Capricorn as well. The rotation of the Earth will also create a deflection of these pressure systems, the high pressure systems, as they start to move towards the low pressure systems, and this is what is called as a Coriolis effect, but watch my other videos for that. So we have temperature at the equator being relatively warm, temperature at the poles being relatively cold. The atmosphere directly above the Earth's surface is heated from the terrestrial radiation from the Earth. Whilst the atmosphere is heated slightly by the solar radiation directly, solar energy coming through the atmosphere. The overwhelming majority is from terrestrial radiation. So as air starts to rise, we'll have the least effect of terrestrial radiation as we gain altitude. We have a temperature decrease as we gain altitude. As the air above the surface, as we get higher and higher in altitude, we'll have less pressure, less physical volume above at an altitude that would actually bear down on it. So whilst the volume increases with, as the volume is the static for a given point above the Earth's surface, as we gain altitude, the pressure decreases. So there are various different reasons why the temperature and pressure decrease with altitude, and these all relate to the gas laws as well. As pressure decreases, temperature decreases. As volume increases, pressure decreases. As volume increases, temperature decreases. So these all follow the gas laws. If we consider at the surface of the equator, we have the highest temperature. As we gain altitude, we are decreasing temperature due to the pressure differential and due to the volume differential also. The same is said at the polar regions. However, we are starting from a lower temperature base point because of less solar radiation and therefore less terrestrial radiation. So the temperatures will be colder, but we'll still have that temperature decrease with altitude based upon a decreasing pressure and a volume that is lesser anyway. So this is how temperature, pressure and volume are affected by altitude. So how does that affect our bodies? Well, if we consider the most vital component when we're breathing, we need oxygen. So gravity will tend to keep most of the oxygen towards the surface of the Earth. So below 18,000 feet, that's where we'll find most of the oxygen. But how we breathe is based upon not so much how much oxygen we get, but it's the pressure differential that enables air to come into our lungs. So, for example, we have a certain percentage of oxygen which our bodies operate on, and we're breathing in air made up of oxygen, nitrogen, and any other carbon dioxide, so on and so forth, and also some of the inert gases that we can find as well. At sea level, there is a pressure differential, a relatively higher pressure outside our bodies than inside or inside our lungs. Therefore, as we breathe in, as we mechanically expand the lungs, therefore air is sucked in by the pressure differential, bringing in the oxygen, and then that oxygen is transferred into our lungs by the alveoli and into our bloodstream as well. So that's how oxygen is delivered into our bodies at sea level. As we gain altitude, the more we gain altitude up to 10,000 feet, so on and so forth, we have a gradually very slight decrease in oxygen. Then after 18,000 feet, we're getting a rapid decrease in oxygen because of the gravitational effect. But we're also, most importantly, getting a decrease in pressure as we gain altitude because of that volume issue above the Earth. As we decrease pressure, therefore there is a less of a pressure differential, therefore we cannot breathe at altitude. At extreme altitude we cannot breathe, but as we gain altitude we will need possibly oxygen via breathing apparatus in order for us to breathe effectively. Now, of course, we can become acclimatized by operating at higher altitudes over a longer period of time. And also, obviously, people do operate at higher altitudes over a longer period of time with their bodies being accustomed. But we, for the short term, we will need breathing oxygen. If we fly, for example, as in the aviation world, as the crew, will require supplemental oxygen, above 10,000 feet and certainly above 13,000 feet, and above we will need that. However, as passengers on an airline, you'll never need supplemental oxygen when we're flying, even though we're flying at 35 to 40,000 feet in some cases when we're going on our holidays, because the cabin pressure is maintained in the region of about 3,000 to 4,000 feet. So it's artificial. We're flying in an artificial atmosphere that enables us to breathe in the normal manner. And then we have oxygen that is pumped into the cabin as well, that enables us to breathe as well. So with altitude, as we gain altitude, if we're just miraculously lifted up, then we will need to have oxygen in order for our bodies and also our brains to function properly. If we don't receive that oxygen, if we're either the concentration of the oxygen or the pressure differential, then we will start to feel physical effects, cyanosis, our bodies will start to work inefficiently, and then ultimately this can be fatal. With oxygen deprivation, we'll also start to have mental incapacity as well. So that can start off very light, very innocuous, and then it will start to take over where we don't actually know what we are doing and we cannot reason properly. So there's a physical and there's a mental aspect. That's why the pressure differential and the oxygen content as we gain altitude is very important, especially in aviation terms, but also if we are working at altitude on the surface, then we have to take into account that vehicles will not work as well at altitude. Our bodies won't work at altitude as well. So that is one thing that we have to be concerned of. So oxygen as we gain altitude will decrease, certainly above 18,000 feet, but it's the pressure differential that we have to be most concerned about, certainly as we're going through the 8, 10, 13, 15,000 feet altitude. So as we gain altitude, the pressure decreases, the volume decreases, the temperature decreases. Temperature decreases because, as I've already stated, very simply, that we're getting further and further away from the hot zone, if you like, from the source of the terrestrial radiation. But what else is happening here? Well, there are a few other factors to consider, and this is to do with latent heat exchange. So latent heat exchange means how heat is transferred in and out of molecules, if you like, in order to affect their state or their condition or their activity. So if we want hyper-energized molecules, we need to absorb heat. If we want lesser energized molecules, we have to release heat. All the molecules do, I should say. So an average, what we call as a lapse rate, the average lapse rate, the average decrease of temperature per 1,000 feet, equates to 2 degrees Celsius for every 1,000 feet, as an average. It's not set in stone. What is this based on? Well, this is based on the pressure differential, how pressure affects temperature as the pressure decreases, but also it relates to moisture, the moisture content, and we have what we call adiabatic lapse rates. A bit of a mouthful that is, but adiabatic lapse rates relates to the temperature decrease as air rises, and that is really affected by the moisture content. So the moisture content will relate to what we call a dry adiabatic lapse rate, where there's less moisture in the air, and a moist adiabatic lapse rate, where there's more moisture in the air. So dry adiabatic lapse rate is in the region of, I know there's some fluctuation, but in the region of 3.5 degrees for every 1,000 feet. So for every 1,000 feet we gain in altitude, we'll lose 3.5 degrees. A moist adiabatic lapse rate is in the region of 1 to 1.5 degrees loss of temperature or reduction in temperature for every 1,000 feet. So why the difference? So you can see the average between the two is in the region of about 2 degrees. So why the difference? Well, the difference relates to how heat is absorbed or released in the way moisture, the way liquid changes its state. If we have water vapor, as it rises, it will start to cool. As it cools, temperature, dew point, convergence, will have condensation. In order for water vapor to change its state from a vapor, a gas, to a liquid, we have to, or the water itself, the molecules have to release energy. So therefore the ambient air becomes heated, in inverted commas. The more moisture, the more ambient air heating. Therefore, the moist adiabatic lapse rate will mean that more temperature is released to the air. Therefore, the ambient air will be heated up, so the lapse rate will be less as you're gaining altitude. With a dry adiabatic lapse rate, there is less moisture in the air. There's less moisture in the air, therefore there is less temperature dew point convergence, which will affect less physical moisture in the air, therefore there's less condensation. Less condensation means less heat is released, part of the water vapor to liquid process, therefore there is less ambient air heating, therefore there is more cooling as we gain altitude. So we have a temperature differential as we're gaining altitude because of less pressure, less volume, because of the gas laws, but also because of moisture as well, and how that affects temperature due to the latent heat exchange. So that's how temperature, pressure and volume relate to each other, and also how they change with altitude. The volume is affected by the solar radiation heating up the Earth, leading to the terrestrial radiation, which causes expansion of the air, which leads to vertically developed atmospheres above the Earth in the troposphere up to the tropopause, and that creates the volume of the atmosphere. The troposphere up to about 60,000 feet at the equator, 30,000 feet at the polar regions, and is bordered by the tropopause at the top. Now the atmosphere is very, very minorly heated by the solar radiation as it passes through the atmosphere. There is greater heating at the tropopause, and there is a temperature differential there. We might see greater heating there. But really throughout the troposphere, this heating comes from the terrestrial radiation as the Earth loses heat. As we gain altitude, because the air is getting thinner, more voluminous, less volume above, as we gain altitude, there is a decrease in pressure. Because of a decrease in pressure and decrease in volume, there is a decrease in temperature as well. Hopefully that explains the relationship between temperature, pressure and volume with a gain in altitude for you. Thank you.